Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1905 represents a pivotal moment in the evolution of physics, a period where accepted understandings of space, time, and matter underwent a radical transformation. While the name theory of relativity often evokes the image of Albert Einstein, the landscape of scientific thought at this time was dynamic, shaped by a confluence of ideas and the contributions of numerous individuals, including those of Max Born and Max von Laue. Although their direct involvement in the formulation of Einstein's theory warrants careful examination, their intellectual milieu and subsequent contributions to this framework offer an important perspective on this crucial period. This essay seeks to dissect the intellectual context surrounding a development of relativity, the specific roles of Born and von Laue, the lasting impact of Einstein's seminal. The late 19th and early 20th centuries presented a significant challenge to classical physics. The success of Newtonian mechanics and Maxwell's equations of electromagnetism had led to a seemingly complete understanding of the universe. Yet, experimental observations, particularly those related to the speed of light and the behavior of charged particles, presented contradictions that classical physics struggled to resolve. The Michelson-Morley experiment, which attempted to detect the luminiferous ether, the hypothetical medium through which light was thought to propagate, yielded a null result, casting doubt on the very foundations of Newtonian concepts of absolute space and time. Furthermore, the observation of the constancy of the speed of light, regardless of the motion of the source or the observer, was at odds with the Galilean transformations, which dictated how velocities should be added in different inertial frames. The Lorentz transformations, developed to reconcile these discrepancies, introduced the concepts of length contraction and time dilation. Their physical interpretation remained Max Born, unlike many of his contemporaries, entered the scientific arena initially with a focus on mathematics and its applications to physics. Born's early work centered on the theory of elasticity, crystal lattices, and the stability of mechanical systems. Although his initial scientific pursuits might seem distant from the realm of relativity, his deep understanding of mathematical physics provided essential tools for subsequent developments. He would, later in his career, become a pivotal figure in the development of quantum mechanics, a field inextricably linked to relativity. He appreciated the inherent tensions between classical physics and the emerging ideas of relativity. His rigorous mathematical approach and his commitment to the foundational principles of physics would prove valuable as relativity matured. Max von Laue, a contemporary of Born's, possessed a comparable intellectual dexterity. Von Laue, whose early work focused on the absorption and scattering of light, became a champion of Einstein's ideas early in their presentation. He possessed an exceptional ability to grasp difficult theoretical concepts. His initial background in optics and electromagnetism gave him a unique vantage point from which to appreciate the implications of Einstein's theory. Von Laue rapidly became a leading proponent of relativity, helping to disseminate Einstein's work through his own research and writings. He was among the first to recognize the importance of Einstein's work and played a critical role in promoting its acceptance within the scientific community. Einstein's 1905 papers, particularly on the electrodynamics of moving bodies, revolutionized the understanding of space, time, and the relationship between them. The special theory of relativity, presented in this paper, introduced two fundamental postulates. The laws of physics are the same for all observers in uniform motion, as the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source. These postulates, seemingly straightforward, led to profound consequences. The theory elegantly resolved the paradoxes that had plagued classical physics. The Lorentz transformations, previously a mathematical tool for navigating experimental inconsistencies, now gained a physical interpretation, becoming the correct way to relate measurements made by observers in relative motion. The theory predicted time dilation, length contraction, and equivalence of mass and energy, encapsulated in the famous equation E=mc. Born's direct contribution to the initial formulation of the special theory of relativity was comparatively small. His focus at the time was directed towards other aspects of physics and applied mathematics. His later expertise in quantum mechanics, however, gave him an indispensable viewpoint regarding the implications of relativity. His work on the probability interpretation of the wave function in quantum mechanics, for which he received the Nobel Prize, relied heavily on relativistic principles. Von Laue's initial contributions, conversely, played a more direct role in validating and popularizing Einstein's work. His deep understanding of optics and electromagnetic theory led him to the critical application of Einstein's theory. In 1912, Von Laue provided experimental confirmation of the wave nature of X-rays. Von Laue's experiments employed the concept of the diffraction of X-rays by crystals. This work provided definitive evidence for the wave-particle duality of light. This confirmed a central prediction of Einstein's theory. This was one of the first significant experimental validations of special relativity. The applications, immediate impact, and subsequent use of special relativity were and continue to be wide-ranging. The initial impact was primarily theoretical, providing a consistent framework for understanding electromagnetism and mechanics. However, the theory's predictions, such as time dilation, were soon experimentally verified. The implications for particle physics were immediately profound, as the theory provided the correct description of the behavior of particles moving at speeds approaching that of light. The mass energy equivalence provided a revolutionary understanding of the nature of energy, impacting fields ranging from nuclear physics to cosmology. The subsequent evolution of special relativity is a testament to its foundational nature. It has been extended, refined, and applied across disciplines. Einstein's later development of the general theory of relativity extended special relativity to include gravity, providing a more complete description of the universe. The concepts of special relativity are fundamental to our understanding of modern physics. It continues to be an integral part of the standard model of particle physics in cosmology, where it underpins the Big Bang theory, and in technological applications, such as the global positioning system, which must account for relativistic effects to function with adequate accuracy. Throughout the early decades of the 20th century, the scientific community grappled with the implications of relativity. The reception of Einstein's theory varied from initial skepticism to enthusiastic acceptance. Von Laue played an important role in popularizing the theory. His work on X-ray diffraction provided experimental validation. This helped to convince the scientific community to embrace relativity. The theory faced its share of critiques. Some physicists were resistant to abandoning the established framework of Newtonian physics. However, the experimental successes of relativity outweighed the concerns. The theory gradually gained widespread acceptance. Born's contributions, while not directly involved with the initial formulation of relativity, indirectly impacted the acceptance of the theory through his work in quantum mechanics. His alone work on the probabilistic interpretation of a wave function in quantum mechanics used relativistic principles, even though the initial development of quantum mechanics occurred concurrently with special relativity. The mathematical tools developed by Born became essential for the development of quantum field theory, which combines quantum mechanics and special relativity. The influences that shaped the intellectual landscape surrounding the development of relativity were considerable. Einstein's work was largely influenced by the earlier work of Hendrik Lorentz and Henri Poincaré, who had independently developed the Lorentz transformations. These transformations, originally developed to explain the null result of the Michelson-Morley experiment, became central to Einstein's theory. Einstein also drew on the work of Ernst Mach, whose critique of Newtonian mechanics emphasized the importance of operational definitions and the relativity of motion. The legacy of the 1905 breakthroughs extends far beyond the scientific community. The scientific and philosophical repercussions of special relativity continue to resonate. Its impact on our understanding of space and time, causality, and the nature of reality is undeniable. The implications of relativity have profoundly changed the way we approach fundamental questions about the universe. The theory has fueled technological advancements, from nuclear energy to the development of GPS systems. The theory's influence is intertwined with culture, inspiring countless works of art, literature, philosophical inquiry. In conclusion, the 1905 paper by Einstein, although not the exclusive domain of Born or von Laue, stands as a landmark achievement in the history of physics. The intellectual backdrop of the time, and the specific contributions of Born and von Laue to the development and dissemination of relativistic concepts underscore this pivotal moment. The enduring impact of this theory is clear. While the theory initially confronted resistance, it swiftly revolutionized our understanding of the universe, offering a new perspective on space, time, and their intricate interplay. The influence of this work has continued to evolve over time. Its profound implications have resonated across disciplines, influencing not only scientific thought but also broader philosophical and cultural perspectives. The theory's lasting legacy solidifies its place as one of the most important scientific achievements of the 20th century.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.